So thank you very much for this very nice introduction, Håkan, and thank you very much to you and the organizers, to David and the other organizers and the ESI staff for inviting me to give a lectures. I feel honored about it. And it's also very nice for me because actually what I have about what I'm going to talk today are things I thought about when I was here in Vienna some years ago for during my sabbatical leave. So it is very nice to be here. So let me tell you about the outline of the course. I divide in 4 parts. So today we'll do part 1 and part 2, hopefully. So part 1 will be just mainly differential geometry. So differential geometry tools, and this will be very pedagogical. So these are things that are well known. I mean, from differential geometry and classical mechanics. So tools that I will review here. Then in part 2, I will use these tools to formulate, to tell you how relativistic kinetic theory should be formulated, at least in my opinion. So it turns out you can do it in a very nice way. It has been, of course, done over the years for many people, especially Ehlers has a nice review articles about this in the past. Okay, but I will review the theory for simple collisionless gas, charged and uncharged. Okay. And then in the next 2 lectures, so I will tell you about how to solve the Vlasov equations or the collisionless Boltzmann equation on a black hole background. So like the Schwarzschild background as an example, and give you a flavor about some results we obtained recently about the mixing phenomena of bound orbits. So this is an interesting phenomena which involves relaxation process. Also, there are no, collisions are completely neglected, and present you some preliminary results about stationary asymmetric tori in solutions which describe this. And then part 4, if we have time, I will like to tell you a little bit also about the collision term, because I think that's something that there's still much work to be done on. So I would like to tell you about the relativistic Boltzmann equation with the collisions, and if there's time, tell you a little bit of the method of moments and an application to Friedmann-Lemaitre-Robertson-Walker cosmologies. So most of this work, I've been privileged to work with many good students, and they had actually during the PhD, very, very nice colleagues and students also, they have helped me to understand these things. So I just want to this is certainly not a complete list of reference, but just a few references that we use actually for I'm using for the course. So there's a very classical paper by Werner Israel, an old one in '63, where he describes the relativistic kinetic theory for a simple gas. So the relativistic Boltzmann equation, basically, and ends with the Chapman-Enskog approximation. Then there's this review by Ehlers I mentioned before, which is also an old work where most of or many ingredients say about the differential geometry already discussed here. Then there's this classical book by Cerciniani and Kramer, which is called the relativistic Boltzmann equation. So this has also many results about special relativistic and general relativistic, the special and the general relativistic Boltzmann equation. And then this 3 articles is things I'm going to take the material of for my course. So first, Thomas Zanias, who is a colleague of mine in Morelia, he actually initiated me to this kinetic theory, relativistic kinetic theory. So we started working on it and realized how nice the geometry was. So we wrote a paper in Class in Quantum Gravity some time ago, where we highlight the role of this differential geometry tools for the formulation of the relativistic kinetic theory of gases. So this was formulated on the tangent bundle, but then more recently we reformulated things, so especially if Paola Rioseco is also here in the conference, reformulate this in terms of the cotangent bundle. So it's equivalent at the end, but the cotangent bundle formulation, as you will see, has the advantage is a little bit more naturally adapted to the Hamiltonian framework of the theory. Okay, so statistical mechanics is usually based on Hamiltonian mechanics, so that's why it's a little bit nicer to have this. Okay, and here with Paula we wrote a few papers, and one of them is this one is about phase space mixing, so that's what I'm going to talk about in today's. And very recently we worked with Ruben and Carlos, and I think they are here online. So if you have technical difficult question, please ask them. So we wrote a review article, a long review, I mean, about 70-page review article, where, and this is going to appear in General Relativity and Gravitation. So we'll review most of the material I'm going to present in the course, except the mixing results of in the part 3 that's going to be based on this article here. Okay, and of course I encourage you, so in this article we put all the original, I mean, there's a huge list of references that and the historical development and so on that I'm not going to go into today. All right, so let's start with part 1 then. So I will start with a brief physical motivation why it is interesting to study relativistic kinetic theory. Then I will tell you about the cotangent bundle, as I said, with the space-time manifold, and the structures, the natural structures that we have here, which is the Poincaré one form, or the canonical one form, the symplectic structure, free particle Hamiltonian, and the Liouville vector field. And then we're going to talk a little bit about horizontal and vertical subspaces, the Sasaki metric. So it turns out you can lift the space-time metric in a natural way on the cotangent bundle, and this is called the Sasaki metric. And then we'll talk also a little bit about volume forms. Okay, so volume forms are not especially important because if you want to give an interpretation of the distribution function, you should somehow integrate, and then you need volume forms. Okay, and the metric will be helpful in the process of this. Okay, so this is quite standard thing. So I did it. Hope it is going to be pedagogical, thinking of the younger participants here in the audience. So I hope it will be useful. Okay, so motivation. So of course, something fascinating I think about kinetic theory, or in general statistical mechanics, is that you try to explain macroscopic phenomena from starting from the microscopic laws of particle mechanics. Okay, I mean, all I'm going to do is to talk about is classical, so non-quantum. Okay, okay, so you have microscopic laws for a large number of particles, and then you somehow, instead of, as Markus Kunzle described yesterday in his course, instead of following each particle, you describe it through a statistical description, so through a distribution function, and then from this you read out like the macroscopic observables, and you get phenomena, interesting phenomena. Okay, so that's probably the most, I mean, the fascinating thing, right, about the theory. Okay. Now on the more practical side, of course, this is important because you can, I mean, it provides, if you want, the justification or fluid dynamics, or you can derive fluid dynamics from kinetic theory, or at least in some regime, the regime of dilute gases. But it doesn't give you just the conservation laws, it also gives you the equation of state, viscosity, heat transport, and phenomena like this, okay? And in the relativistic case, this is still this is a highly non-trivial issue. I mean, this has motivates a lot of theories. I mean, this is Stewart theory. Irreversible thermodynamics is also extended thermodynamics by Ruggiero and Müller, for example, or divergence type fluids that have been looked at by Geroch, Lindblom, and Reula and other Nagy and other people. So this has, and this was largely motivated by kinetic theory. But how there's still no consensus, I think, of what is the best theory, and still this theory most of the time they try to describe near equilibrium configurations. Okay, then as we heard yesterday, galactic dynamics is also most of the study is based on kinetic theory. So if you want to model a galaxy as a whole, usually the Newtonian description is sufficient, but eventually we know now that in the center of most galaxies there's a supermassive black hole, and then at least when you get to the vicinity of this black hole, then the relativistic effects will be important. Okay, so you cannot get away with the Newtonian description. But also, for example, in plasma physics at very high temperature, for example, like a fusion reactor like ITER, which is built in France, there are also relativistic effects expected to be important. Also, that the gravity side is probably not that much important, but at least the special relativistic effects. And then there's also plasma physics, but at very high, not only at very high temperature, but also in a very strong gravitational fields. So for example, like if there's plasma around a black hole, like an accretion disk around supermassive black hole, or also in the case of cosmology of the early universe, and they couldn't resist to put this picture on the first image of the shadow of the black hole a few years ago, which was from the Event Horizon Telescope. So this is quite a spectacular result. So this is not a cartoon, but this is actually an image. And so with an array of radio telescopes, they got enough resolution to take a picture of the center of the galaxy M87. And it's at a scale, they have enough resolution that they could take the picture at the scale of the event horizon radius of the supermassive black hole that one is expecting there. Okay, and then this is the angular resolution, so that corresponds to give you also and a colleague who is an astronomer was involved in this collaboration in Morelia. He told me that's about like comparable to taking the picture of an apple at the surface of the moon. So that's the resolution they have. So it's quite impressive. Okay, and so you see here the black hole shadow, and by measuring the size of the shadow, they have this estimate for the black hole mass. So it's a giant black hole of about 6.5 times 10 to the 9 solar masses. And okay, and soon there will also be results about Sagittarius A stars, or the center, the black hole in the center of our galaxy, which is 1,000 times lighter, but is also 1,000 times closer. So the angular resolution is about the same. Okay, and I think that's really cool, because that's really is also nowadays, so that's really a regime where you have plasma, which is both at very high temperature and in a strong gravity region. So not only is this, mathematically interesting, but it's actually, now we have observable, we are getting observable data about this regime. All right, so that was the motivation. Now a few more things before we start. So how should we formulate relativistic kinetic theory? Well, first of all, we know general relativity is a geometric theory, so you have this principle of general covariance, and that requires a covariant formulation, as Einstein taught us. And the easiest thing to incorporate this, to have this manifestly, to have the covariant formulation built in, so to say, is if you, formulate things in terms of differential geometry, and then you don't have to verify how things transform the coordinate transformation and so on. That's all for free. Okay, now for many, but not all matter models, many times sufficient to work on the space-time manifold. For example, if you work with scalar field, electromagnetism, or a perfect fluid, then usually it's sufficient to study the geometry of the space-time. Yeah, I mean, or maybe something derived from the space-time manifold and other quantities from the fluid. But for relativistic kinetic theory, so what is central is a phase space. So you need like a geometric description of what phase space should be. Okay, and that is done through the tangent or the cotangent bundle associated with the space-time manifold. Okay, so next to at each event, you want to look at the space of all possible momenta, and that gives you it leads you naturally to the tangent or cotangent bundle. Okay, as I said before, so in this course, I will put emphasis on the cotangent bundle, where the momentum is regarded as, I mean, you think about the canonical momentum, and then which is a covector, okay, and then this leads you to the cotangent bundle. All right, so a few conventions and notation before we start. So mg, I will assume it's a 4-dimensional smooth, so C infinity smooth Lorentzian manifold, which is connected and time-oriented. So time-oriented because you want to say that the particles move towards the future.
Yeah.
The signature convention is minus plus plus plus. So Txm and Tx star m will denote the tangent and cotangent space at event x. And so Fn, Xn, and lambda Pn will denote the class of smooth functions, vector fields, and p-forms on the manifold N. So for p-form omega, d omega will denote the exterior derivative. So this operator d that converts a p-form into p+1 form. So for a function is df is just a differential of this function, which is a 1 form, and so on. And here d squared is 0. And then ex omega, that refers to the interior derivative with respect to the vector field x. So that's just taking this p form and plugging into the first entry the vector field x. So that converts a p form into a p-1 form, and ex squared is 0. And then a formula which is very nice is this Cartan formula for the Lie derivative. So if you take the Lie derivative of a p form with respect to x, you can write this as d ex omega plus exd omega. Okay, and this is something very, very handy, especially for the Hamiltonian formalism, as we're going to see now. So Greek indices are going to be space-time indices from 0 to 3. Latin indices are going to be space indices, and sometimes I'm going to use tetrad indices. They will be indicated with a hat. Now we're going to work in geometrized units where the gravitation constant and the speed of light are 1. So time is length and this mass are measured in the same units. All right. Okay, so let's start. So what is a cotangent bundle? And a cotangent bundle is a pair of xp, where x is an event and p is a covector at that event. Okay, and then there's these natural projections, or pi just takes a pair xp and basically it erases the information of p, so it's also x. So here's a little picture. So you have the m, the manifold, an event, and then p to the minus x, so that will be the fiber over x. So that's the space of all p's at that point, of all covectors at that point. Okay, so that's, and then you can, that's what I just said. So this fiber is basically the same as the cotangent space at x. And then what you can prove is that this is again a manifold. This is an 8-dimensional manifold. And it's actually orientable automatically, even if the m is not orientable, this is automatically orientable. So by the way, I didn't say that, but I consider dimension 4 just for definiteness, to simplify the notation. But in the article, we did it actually in d dimensions or n dimensions. So there's no obstruction to that. And if you have never prove this lemma, and I encourage you to do so because it's nice. So the idea is very simple. You take a chart, a coordinate chart on M, okay, where you have local coordinates x mu. And then if you take a covector here, you just decompose it into dx mu, okay, which will be the basis, the associated basis on the cotangent space. And p mu you can actually compute by evaluating p at d by dx mu, okay? So that's and x mu, p mu, that gives you local coordinates on this tube here, okay, so on p minus 1 of u. And now what you have to do, and that's the first exercise, I put in little exercises that I encourage you to work on if you are interested in learning this formulation. So now if you take an atlas of M, so some charts that cover M, then you should verify that the transition maps, they are C-infinity differentiable, and that's the first exercise. So you just have to do the pictures. We have two overlapping charts with the corresponding cylinders, and then you map a point from here to here. And then you should verify that this map is differentiable. And then more or less, here's the hint, or the result will look something like that. If you compute the, I mean, why it's orientable, I mean, you should answer this too. So if you look at the Jacobian, so it has this triangular structure. So here you have a matrix M, and here you have the inverse transpose of M. And then when you compute the determinant, this will be 1. So it's actually, so this atlas that you get is not only oriented, but it's also volume preserving, and we'll understand why in a moment. All right, so now what you can do once so now you can take an arbitrary vector field on the cotangent bundle, and you can decompose it into the coordinate base. The differential of the projection map will be, you can use it, you can take it to project this vector field down to the to a vector on the manifold. So it will just kill these p components here. And now comes the definition of the Poincaré one form. So what you do, so there's a one form, so you give it here a vector field, you evaluate the vector field, and what this does, you first project the vector field to give you a vector on the manifold on at x, and then you evaluate p on it, okay? And that gives you a number, okay? And that's linear in x, so this defines a one form. And the symplectic form is just a differential of theta, so it's a two form. And now the exercise 2 consists in showing that in terms of this adapted local coordinates, theta is p mu dx mu, so that's very simple from these two equations. And then when you take the differential of this, so omega s will be dp mu dx mu. Okay, and now you can verify that omega s is a closed non-degenerate 2 form on the cotangent bundle. So that means that this is a symplectic manifold. And okay, the first is very easy because omega was a differential of theta, so d omega is 0. And now to show that it's non-degenerate, you evaluate here one of the entries at x, and that gives you this one form here. This gives you x mu dp mu minus y mu dx mu. And now you see that this is 0 only if x is identically 0. So if x mu and y mu is 0. It's non-degenerate, okay? And now comes the next definition. So you have the symplectic form, so you can, so given a function on the cotangent bundle, there exists a unique vector field, which we call xh, which is called the associated Hamilton vector field, which is dual to the gradient of h. So dh is omega s with xh in this entry. You can write in terms of the interior derivatives like this also. And explicitly in terms of local adapted local coordinates, so you just use this formula, and then you find this formula, this explicit formula that you recognize from Hamilton mechanics. Okay, so the integral curves of xh, they satisfy this equation, and these are just the equation, Hamilton's equation of motion. Okay, so you have a geometric way of rewriting these things. Now, one immediate consequence of the Cartan formula I was advertising before is that you can show immediately that any Hamilton vector field preserves the symplectic structure. Okay, so otherwise it generates a canonical transformation, and this is simply you apply the Cartan identity to it. So you know d omega is 0, so this term goes away. And here you use the definition of xh, so this is minus d squared h, but d squared is 0, so this is 0. So this is completely trivial. Now you can also introduce the Poisson brackets between two functions on the cotangent bundle. And this is just the symplectic form evaluated at the corresponding Hamilton vector field. Okay, but this gives you the change of G along the flow of H, or minus vice versa. Okay, so okay, and now this exercise 3, so you can verify the following properties of Poisson bracket. So it's antisymmetric, that's trivial from the definition. It is linear in the second argument, and then it satisfies this Jacobi identity. And in adapted local coordinates, you get this familiar expression. Okay, now let's move on and let's come to the let's introduce the free particle Hamiltonian. So that is the one that will generate the motion of free test particles, say, and moving on the curved space-time. So the free particle Hamiltonian is just 1/2 p squared. So now comes in the metric. So you have here the inverse metric at x, and you contract this with p nu. And if you work out what the associated Hamilton vector field is, so that's called the Liouville vector field in this particular case. So you get this expression here. And the next exercise is to show that the integral curves of L, when you project, so these are integral curves on the cotangent bundle, and when you project them down to the manifold by means of the natural projection pi, you can show that these curves here satisfy the geodesic equation of motion for an affine parameter. Okay, so you have here geodesics. You can have geodesic that cross at a point, but they may have different. If they have different momenta, I mean, then when you look here upstairs, they will not cross actually, because P1 will be different than P2. So here they do not cross, but they will cross here. All right. Now, so the relativistic Boltzmann equation for simple gas, you can write it in this form. I will explain all this in more detail, but to give you the to give you a preview, say, so there is this transport term here. So this is just a Liouville vector field applied to F. F is the one particle distribution function. And then the collision term will be a term that is quadratic in F, which involves some integral. That's called the collision term. And if you set the collision term to 0, then you get the Vlasov equation. All right. Now I should say something more. And something I haven't taken into account yet is that, well, first, we are for gas particles, they should move on time-like geodesics. And not only on time-like geodesics, but future time-like geodesics or future null geodesics in case you have a photon gas. Okay, so you get a further restrictions if you consider a simple gas where all the particles are identical, so they have the same mass. Then this momentum is not arbitrary, but it should satisfy that p squared is minus m squared, where m is the rest mass of the particle. Okay, and that leads you to, so P should be restricted to what is called a future mass hyperboloid. So P is a covector and P squared is minus M squared. And then if you raise the index of P, so you construct the corresponding vector, this should be future directed, okay? So you want to gas particles to follow such P's. Okay, in the future mass shells, also that's a subspace of the cotangent space at X. But if you vary x, now you get the future mass shell. So this is the pairs xp, where x is an event and p is restricted to px, to the future mass hyperboloid. So that's called the future mass shell. And that's a space or a subset of the cotangent bundle. Okay, now you can prove that if the mass is positive, then this is actually a 7-dimensional submanifold of T star M. And further, the Liouville vector field L is tangent to the mass shell. And the proof is very simple. If you note, you just have to notice that this is a level set of the free particle Hamiltonian, okay, because here H is constant because of this condition here. Okay, and then the differential or the gradient of H is dual to L. Okay, by definition, and L is non-zero if M is positive because P cannot be zero then, okay? So the gradient is non-zero, so this is a regular submanifold of codimension 1. And to show that the Liouville vector field is tangent to it, it's also very simple. You just look, I mean, you take the gradient of H and dot it with L basically, and this is, again, by definition of the H is minus EL squared omega S, and this is 0. Okay, so you see this differential calculus formulas are very powerful. You get all these statements trivially, I mean, very easily. All right, so let us move to the next geometric structure. So what we're going to introduce now is at each point in the cotangent bundle, we have the tangent space at this point. So this is a tangent space at point xp of the cotangent bundle, okay? And now at each point, there is a natural split into horizontal and vertical subspaces. So these are 4-dimensional 4 spaces, subspaces of TXP. And how do you define them? The one is the vertical space is easy, so that's the kernel of the differential of pi. Okay, so this consists, in other words, of all vector fields that are projected to 0. So this is tangent to the fibers. And then there is this other horizontal part, which you can also define as a kernel of what is called the connection map, which I will explain in the next slide. Okay, so they both have full rank. So this is these maps. So the kernel is 4-dimensional. Now, what is so here you have a natural basis, which is just these vector fields here, d by dp mu. So these are 4 linearly independent vectors that span the vertical space. Now, what about the horizontal space? So now to explain this, I introduce the connection map, and that works like this. So I want to define the action of the connection map on a vector field z. So I take a vector field z in the cotangent bundle, and I imagine I have a curve here that is tangent, that passes through xp, and that is tangent to z at xp. Now this curve, because I'm the cotangent space, so remember these are pairs of points. So this curve has, I can look at as a curve x of lambda, p of lambda, where x of lambda is a curve, gives rise to a curve in M, and p of lambda. So at each point x of lambda, that gives me a covector. So that's, you can imagine like a covector field along this blue curve. Okay, and when lambda is 0, so x0 is x and p0 is p. Okay, now the connection map is defined as follows. So you take this field p of lambda, and you take the covariant derivative. So covariant derivatives with respect to Levi-Civita connection on the space-time in the direction of the tangent vector to the blue curve here. So this is red vector here of p lambda. Okay, so this is so this gives you another vector, and that is called k of xp of z. Okay, that's how it's defined. And now that's the next exercise. So if you decompose this in a coordinates, I mean in the basis of adapted local coordinates, you can show that explicitly this is given like this. So if you have a, if Z, you decompose it into the X mu and the Y alpha components as before, then this Z will be Y alpha minus, and here into the Christoffel symbols, E nu X mu. Okay, so these are the Christoffel symbols. So this is how you can compute this connection map. Okay, and from this expression, you see also that this is independent on the choice of the curve here. And it's also a linear map. And now from here, it's also easy to see that you get a basis of horizontal vectors. You just have to put this equal to 0, and that will give you a relation between Y and X. And that gives you these 4 vector fields here, which we called capital D by dx mu. Okay, so you have 4 vector fields that span this here, and obviously these are linearly independent from this. Okay, so this gives you the split. What is also useful is to introduce the dual basis, dx mu and capital dp mu. So this is the dual basis to these basis vectors here. And then any tangent vector, then you can decompose in a unique way in a horizontal and a vertical part. And like this, okay? Or, yes? Here. Oh, sorry, so Z is a vector here. Okay, and K of Z, sorry, it's a covector, so it gives you a covector as X. Yes.
They want me to repeat the question?
Yes, please.
So my question.
Okay, so the question was what K of Z is. So K of Z is a covector at X on the manifold.
Covector.
A covector, yes. It's a covector, right? So P of lambda, that's a covector field. Okay, so you differentiate this, you take the covariant derivative of this, so that gives you a covector. I probably said it wrong. I said it's probably said it's.
No, I was confused. I didn't see the P of lambda in the formula. Yeah, this
so
is
the
a
P lambda
covector.
is a covector field here. Yes.
Thank you.
Okay, thank you for the question. All right. So we have this split, and now, here's another exercise for you, so you can compute the commutator of this. Okay, so there are 3 commutator, 3 groups. So the commutator of these are trivials, of course, but those one are not trivial. And if you compute the commutator of this gives you the curvature. This gives a term, a vertical term, including the curvature. So that shows you actually that the horizontal space as a distribution is actually non-integrable in general if the Riemann, if the curvature is non-zero. And then you can also compute this commutator here. Okay, and here's another exercise. So you can show that the symplectic form, so the little d you can replace by capital D. So that's easy to see because the difference between two is just this Christoffel symbol term. And then if you use the fact that this Christoffel symbol is symmetric in beta mu, you see this immediately. And furthermore, you can show that the Liouville vector field you can write in more compact form like this. So that turns out to be a horizontal vector field. All right. Now, so besides this split in horizontal and vertical vector subspaces, it gives you this connection map gives you more. It also allows you to identify both H and V, so the horizontal and the vertical space, with the tangent space or the cotangent space. Okay, and so this is very simple. So you just introduce this map IH, which goes from the horizontal space to the tangent space, and you just so you take a horizontal vector and you project it with d pi. Okay, so this invertible, because remember that ZH is in the kernel of K, but not of d pi. And vice versa, you can define this vertical map IV, which takes vertical vectors to tangent vectors at X. And here you use the connection map to do this projection, and then you convert it into a vector, the covector from vector with the inverse metric. So you raise the index if you want, and that gives you a vector here. Okay, so these are linear invertible. And now that allows you to define what is called an almost complex structure. So you can think of it as like a rotation in this tangent space. So you rotate horizontal vector into vertical vectors. So that's what's indicated here. So you take IH and then you take the inverse of IV. That gives you a vertical vector, and J of Z vertical, that will be minus. So you map this into minus this one like this, and you can show that this map, the square of this map is minus the identity. It's like a 90-degree rotation you can think of. Once you know all this, now it's very natural how to define a metric on the cotangent bundle. So, and that's called the Sasaki metric because Sasaki did that in 58 in the context of the tangent bundle of Riemannian manifolds. And you define this metric in such a way that the split we have just introduced is orthogonal, but also that these maps IH and IV are isometries. So in other words, let's call this metric G hat. So G hat evaluated at Z and W. So you can decompose this in horizontal and vertical, but we require that the vertical components are and the horizontal one are orthogonal. So that should be the same as this one. And now this horizontal vector fields, you can convert it into vector fields on the space-time manifold by means of this map IH. We have this one, and here the same for the vertical components, okay? And more explicitly, you can write it this way. Okay, so that's called the Sasaki metric. Everything is defined completely geometrically. So it's, and now you can also check that this J that I just introduced before is an isometry for this metric. Now, it's also a very easy exercise to, if you compute the components of the metric in these adapted local coordinates, then you can show that you can write it in this way. So it's G mu nu dx mu dx nu. So that's the space, the part of space-time if you want, and then you have this term here, which corresponds to the vertical part, if you like. You have the inverse metric, but remember that this D capital dp mu includes here the Christoffel symbols. Okay, so this is a metric with signature. So it has 2 time directions and 6 spatial direction, and the determinant is actually of the metric components is 1 in these coordinates. Good. So a few properties of this metric. So what you can show from previous exercise easily is that if you take the dual of the Liouville vector field, so you evaluate the metric at L. Now L, remember, has only a horizontal part that will just give you this term here. And now that gives you P nu dx nu, and that's actually the Poincaré 1 form. Okay, so the Liouville vector fields is a dual of the Poincaré 1 form. Okay, and then here's the next exercise. So you can show this proposition. So now you have on the cotangent bundle, we have this triple of we have the Sasaki metric, the symplectic form, and this almost complex structure. So this map J, this 90-degree rotation, and they actually relate to each other. So you can show that the symplectic structure evaluated WZ is G hat evaluated WJ of Z for any 2 vectors on the cotangent bundle. So you forget one of them, you can reproduce the third one. And another nice property is that you have now a metric on the cotangent bundle. You have the Liouville vector field, and you know the integral curves of the Liouville vector field when you project them on the space-time manifold. That's an exercise you have to verify in case you don't know it, but that I told you about. But I told you that they describe geodesics on the space-time manifold. But you can actually ask yourself if the integral curves on the cotangent bundle, the integral curves of L are themselves geodesics with respect to the Levi-Civita connection with respect to G hat. And it turns out that yes, the answer is yes. So you can show that the acceleration, if you want, of L is 0. And you don't need to compute the Christoffel symbols to do that. There is a simple proof. So the first thing you notice is that if I take this formula here above and I plug again L inside it, so you have GLL, this will lead twice the Hamiltonian on one hand, okay? Now on the other hand, if I compute what is the covariant derivative of the Poincaré one form in the direction of L, so this you can rewrite as the ELD omega plus 1/2 d of this here. So you can check this identity. But now this is 2 times h, so the 1/2 goes away with the 2. So you get here dh for this term here. And here on the other hand, d omega, you know, d theta, sorry, that is a symplectic form. So EL omega s, and you know this is minus dh. Okay, so this is minus dh by definition of L, and this dh, so this adds to 0. Okay, so this is constant along L, but this is dual to L, so this implies this. Okay, so this is the sketch of the proof. All right, now let's go back to the mass shell. So we recall that for kinetic theory, not the whole cotangent bundle will be relevant, but only this 7-dimensional submanifold. So you have the Sasaki metric. Now you can induce the metric on gamma m plus. And if you do that, then you lose one of the time direction. And then, so that means you are back in the realm of Lorentzian geometry. Okay, so this metric you can show is Lorentzian metric, and the unit normal vector field is given by this expression. So it's 1 over m j of L, or you can write it explicitly like this. And here I've chosen orientation such as h decreases along n, so h becomes more. H, remember, is minus m squared half. It becomes more negative if you go along n. And okay, you can work out the proof. So you remember that you know that n is dual to dh because this future mass shell, I mean, was a surface h constant. So you should look at dh. And then you use this identity I told you before. So that tells you immediately that j of L is parallel to the gradient, and then you just need to work out the normalization. And the normalization, if you plug this in and use that j is an isometry, you get this, but this is p squared, which is -1. So n is time-like, and now if you divide this by m, then this is the right normalization, and then you have proven the proposition. A nice corollary is that any horizontal vector field will automatically be tangent to gamma m plus. Okay, because n is vertical, you see from this expression. But any horizontal vector field will be orthogonal to n, and hence tangent to gamma m plus. In particular, the Liouville vector field, as we already knew. Okay, and then the result I told you before, that L generates, I mean, geodesics on the cotangent bundle that you can immediately now translate to the mass shell. So you have the mass shell with the induced metric. And if you take the induced connection, then you will find that since L is tangent to it, it will also be geodesic on the mass shell. Okay, so everything works fine and then nicely. All right, so finally, let me talk a little bit about volume forms. So we'll need this. So because you have the metric, then there's the natural volume form, which is defined up to the sign, maybe. So we know that in these adapted local coordinates, it's simply this one. But you know the determinant is 1 in these coordinates. So this goes away, and then you get this expression here, choosing a suitable orientation. And now comes the next exercise. You can, so just by reshuffling, I mean by permutating these one forms and summing, you can prove that you can rewrite this volume form as a, I mean, 4 times the wedge product of the symplectic form. Okay, and then you have to divide by 1/4 factorial. Okay, so you can check easily that this same as this, it's just algebra. And why is this nice? Because remember I told you that the Liouville vector field, because it's a Hamiltonian vector field, it will leave invariant the symplectic structure. So this is 0. And then as an immediate consequence of this, one has Liouville's theorem. So the volume form is invariant in the flow generated by the Liouville vector field, because if I take the Lie derivative with respect to L of this, so this will be 0, okay, because of this condition. So this is an immediate consequence once you notice this. Okay, and this too, you can project it down to the mass shell. So on the mass shell, the induced volume form, simply you plug in, so you have 7 vectors. It starts with 2. That's why it ends with 8. So you have 7 vector fields here, tangent to the mass shell, and simply, so you take the volume form on T star M that I just defined, and you plug into the first entry N. So that's the interior derivative. Okay, so that's the definition of the induced volume form. So we have already, we know what this N is, so you can compute this, and now you can show that this volume form too is invariant with respect to the flow generated by L. And the proof is almost direct. There's just one thing. So if you compute the Lie derivative of this thing, then you get that this is the Lie derivative of T star M, which we know is 0. Then there's an additional term that you have to analyze. So there's the volume form on T star M, which is evaluated at, so you need here the Lie derivative of N along L. And then you have these 7 tangent vector fields here. So let's compute this. So if you compute this, it's just a commutator of L and N. So you can plug in the explicit expressions, for example, this one here. And now you can do the calculation, compute this commutator, and what you find is minus L. Okay, so it's not 0, but it's L, and L is horizontal. So it's a tangent to gamma m plus, okay? So here you have 8 tangent vectors, but this manifold we're working on is 7-dimensional, okay? So necessarily they must be linearly dependent, and therefore, because it's totally unsymmetric, this vanishes. So this is the only non-trivial ingredient that you have to look at, but at the end you get Liouville's theorem was on gamma m plus, okay? So Liouville's theorems will actually be very important to derive the Vlasov equation. I will tell you why soon. Okay, and then you can compute these volume forms also more explicitly. And for this, it is not absolutely necessary, but it's advantage. I mean, it's an advantage to introduce an orthonormal frame of vector fields, so at each point, a tetrad, if you want, with the dual frame. And now this covector you expand in terms of this orthonormal frame instead of the coordinate base. Okay, and the advantage of this is just because then the mass shell condition is more easily imposed. So then the mass shell condition just reads that P0 is minus the square root of m squared plus P, the spatial components of P squared. Okay, the minus here comes from the fact that, also remember, to be future directed, that means when I raise the index, then this should be future directed. That should be positive. Okay, so if I lower the index, I have this, get this minus here. That's where it's come from. Okay, but this is now very easy to characterize the future mass hyperboloid or the mass shell. And first, so you can compute now the induced metric from this condition, and then you get this expression here. And if you compute the determinant of this, then you get that the volume form on the future mass hyperboloid will be this expression, which I will call d vol x of p. And this is actually just a standard Lorentz, I mean, the well-known Lorentz invariant form that you know from special relativity. Okay, so you can do the same thing if you don't work in an orthogonal base, but then this expression will be slightly, yes?
And the number 3, dp3?
That's right. So these are orthogonal.
In the line above.
Oh yeah, very good eyes. There's a hat missing here. Yes, thank you. Yes, thank you. Yes. Okay, and then you can do the same now for if you go back to the Sasaki metric. So you can start from the Sasaki metric, and by imposing again this mass shell condition, you can compute explicitly the induced metric on the mass shell. And now here the only complication is that here you have this covariant dp, which involves the Christoffel symbol. So here when you go to an orthogonal frame, you get here connection coefficients, which are defined in this way, but there's no major complication to it. And then you can compute here the induced metric in these coordinates. We have here still the space-time part and here the vertical part, if you like. And now by computing the determinant of this, you get the induced volume form. And you can, so you see here, you have basically what you have here is the volume form on the space-time manifold. And here you have m times what I call d vol before, the Lorentz invariant volume form. Okay, so that means you get this nice Fubini type formula. So if I take an integral, Lebesgue integral function, say, and you over the mass shell, the future mass shell, and the integral of this, you can write it as an integral over the fiber, which is the future mass hyperboloid. So integrate first over p, and then over m, and then there's this mass term here. Okay, so that will be very useful, and I think I'm just on time to finish part 1. Or maybe you can take a break.